Okay, this is section 7.6 from James Stewart Calculus Early Transcendental's book, and we are discussing techniques of integration. And now that we have completed all of the major techniques of integration using things such as direct methods, algebraic manipulation, use substitution, integration by parts, integration using trig substitution, and partial fractions, we're now going to talk about integration using tables. So there are tons of tables of integration available on the internet. In most calculus books, there's usually a reference page in the back of your textbook that lists maybe 100 to 150, maybe even 250 tables of integrals. And usually we try to get students and people to memorize the first 20, which are known as the basic forms. So now we're going to use the extended table and learn how to apply those. And many scientists in the real world, they don't go back to integration by parts and partial fractions and stuff. They, in general, your physicists will focus more on their projects and their complex projects than in calculating a long drawn out trig substitution, for example. So they will often, when they set up their integrals that represent the value that they want to calculate, they'll go to a table of integrals. So it's a very useful technique to learn how to do. So here we go. I've already, in these couple examples, identified the table entry that best matches the integral that I want to integrate. And you'll see in a lot of various tables of integrals that they break out common themes. So you'll have stuff like integrals involving linear expressions a plus bx or a plus bu. Usually they'll tend to use the u variable to suggest that perhaps you might need to make a simple u substitution before you proceed with using a table. All right, so looking at a, we've got the integral of x times the square root of 7 plus 5x, and I see that I've got a table entry that looks very similar to that, and I can automatically apply what I see, and I see that u would equal x, a would equal 7, and b would equal 5. And so now I can apply the formula on the other side, and just having u equal x, I already see that du is going to equal dx, and so I can immediately just make the substitutions. So I see down here that my integral is going to be 2 over 15 times b squared times 3b times u minus 2 times a plus bu to the 3 halves plus c. And I can go back and substitute the values that I have. So b squared, b here is 5, and 3 bu, b again is 5, and u is x, minus 2a, a is 7, and then we have a plus bu, a is 7, b is 5, and we want to take that u and replace it with x, and then we can go forth and simplify, right? So we would have 15 times 25, and 25 times 15 is 375, so we would end up with 2 over 375 times 15x minus 14 times 7 plus 5x to the 3 halves plus c. Good. All right. In this next one, I see that I might need to make a few adjustments in my original integral, but I can see that this is a u variable times a linear expression. And if I just rewrite 4 over 2t minus 7t squared, I can move the 4 on the outside. And I end up with 1 over, and if I factor the denominator, I would get 2 times, or t times 2 minus 7t dt. So I can see here in looking at my expressions u, a, and b, if I let u equal t, then du is going to equal dt, right? And if I see that a here is equal to 2, and b here is equal to minus 7. Because we have 2 minus 7t is 2 plus negative 7t. So I can automatically use on the other side these variables, and let's not forget that we are multiplying entirely by 4. So we would want to multiply this expression by 4. And yes, you can go ahead and include the plus c in the multiplication times 4, but remember that c is an arbitrary constant, so 4 times an arbitrary constant is going to be another arbitrary constant. So we can just leave the c on the outside of that. So I get 4, 1 over, and what is the value of a? The value of a is 2. And we have times the ln. The value of u is t. A is 2. B is minus 7. And u is t, and we can complete our absolute value, we complete our multiplication, and we have plus c, and so our final answer here would be 2 times the ln of t over 2 minus 7t plus c. All right, this one is, you might not see it readily, but it is a little bit trickier. So it's about identifying your proper value of u, but then also making that proper substitution. So the first thing that I see is that I have a u squared in here, and I have a u squared in there. And whatever I let my u equal, it's got to be that in both places. So I'm first going to make a observation here that underneath the radical 9y squared does equal 3y quantity squared minus 5 squared. So I can see that if I'm going to match the u squared minus a squared, I'm going to want to let my u equal to 3y. So I still will have to make a u substitution for du, and my du here is going to be 3 dy, right? And I'm wanting to, and that means that dy here is going to be du over 3, or if I just go in my original integral, if I multiply by 3, I will need to divide by 3, right? And that way I would get dy, 3 dy is going to be my du. Good? I also see that if I'm going to let 3y squared equal u, and I'm going to have my u squared over here as well. I have a y squared up at the top, but I see that 9y squared does equal 3y squared. So if I multiply by a 9 here, I will be able to replace that with 3y squared. And that's going to be a u squared, right? So if I multiply by 9, then I'm going to need to divide by 9 as well on the outside so that I'm only multiplying by a 1, right? 9 divided by 9 is 1. So now I'm ready to transform my integral, and my integral is going to be 1 over 3 times 9, which is 27, times the integral of 3y squared, which was that 9y squared, and 3y quantity squared is going to be u squared. And my du is going to be, and I can actually say it's du because we have 3 dy. And on the denominator, I have u squared minus 5 squared. And now I can apply the other side of my integral, and I'm going to make sure that I multiply by 1 over 27 throughout, because that's on the outside of my integral. And I have over 2, and I have my u squared, and I have u squared. A here is 5, so this would be minus 25, plus, again, a is equal to 5. And so we would have 5 squared, which is 25 over 2, times the ln of u, plus the square root of u squared minus 25. And we can multiply there and add plus c on the outside. I now want to back substitute for u because we started with an integral in x, so we want to end with we started with an integral in y, so we want to end with an integral in y and not in u. So we want to back substitute the u equal to 3y, and so we're going to end up with 1 over 27, and our u is 3y. Our u, this is going to be 9y squared minus 25 plus 25 over 2 times the ln of, and u is 3y. And we have 3y quantity squared is again 9y squared. And we can do plus c. Hopefully that is clear. Sometimes you need to make a u substitution before. Again, here's one, and usually in the big bad table of integrals, there's usually a section on trigonometric integrals, or integrals that contain powers of trigonometric functions, and this is the case where we have tangent to the 5th times pi theta. And I'm going to make a u substitution. Again, that's reinforcing the u variable in the standard tables of integrals. So first I'm going to say let u equal pi times theta. Then du is going to be pi d theta. And so I need a pi in my original integral, which means if I'm going to multiply by pi, I'm going to want to divide by pi. I also, if I want to, I can change my limits of integration. When theta here is equal to 0, u is going to be pi times 0, which is 0. And when theta here is equal to 1/4, u is going to be pi times 1/4, which is pi over 4. So if I am going to evaluate that integral, now I don't have to back substitute for u since I've changed my limits of integration. So in transforming this integral into b in terms of u, I get 1 over pi times the integral, and I'm going to use my new limits of integration, 0 to pi over 4, and I have that my power of n here is going to equal 5. So we're going to use that n and use that 5 everywhere that we see n as a natural number. But back to calculating or transforming my integral to be in terms of u, I get tangent to the 5th times of u du. So let's not forget that we are multiplying the entire integral by 1 over pi. So we multiply our entire evaluation by 1 over pi. And right now we have that n is equal to 5. So on the other side, I'm going to say this is 1 over 5 minus 1, which is 4, times the inverse, or times the tangent of 5 minus 1, which is 4. And then I have minus the integral of tangent to the 5 minus 2, which is 3, u du. Okay. Now, and plus c, but we don't need the plus c since we are still using 0 to pi over 4. I see here that I have another power. It is a reduction type formula. We have reduced the power of tangent from 5 to 3. And so now I'm actually going to change my n, and I'm going to repeat this formula. And I'm going to say now my n is equal to 3. Good. And so we want to, in this integral, use the same formula from above to calculate. So I'm going to keep my equal signs. I'm going to keep everything else in order. And I have 1 over pi times 1/4 tangent to the 4th of u minus, and I'm going to start replacing. Good. And now my n is equal to 3, and I'm still using that formula on the other side. So I get 1 over 3 minus 1, and 3 minus 1 is 2. And I have tangent of 3 minus 1 is 2u. And I have minus the integral of tangent to the 3 minus 2, which is 1. And so that is just tangent of u du. Now I'm going to distribute the minus. And I'm going to get 1 over pi times 1/4 tangent to the 4th of u minus 1/2 tangent squared u, minus minus turns into a plus, of tangent u du. And we also have in the basic table every single trigonometric function to its power, or just standard trigonometric function. So I can evaluate this from the basic table, from the first 20 usually in every table. So I get 1 over pi times 1/4 tangent to the 4th u minus 1/2 tangent squared u plus, and if you check that basic table, we'll get the ln of the absolute value of secant u. Good. And now we get to evaluate using our fundamental theorem of calculus. We don't need to back substitute for u because we changed our limits of integration to be in terms of u. And so we can do our f of pi over 4, take away our f of 0, and our f of pi over 4, remember that tangent of pi over 4 is equal to 1, and let's remember that tangent of 0 is equal to 0, and we also have a secant u, and we know that secant is 1 over cosine, and the cosine of pi over 4 is 1 over root 2, so secant of pi over 4 is going to be just root 2, and secant of 0 is going to equal 1, because that is 1 over cosine 0, and cosine 0 is equal to 1. So those will be useful values, and here we go. So this is going to equal 1 over pi, 1/4, tangent to the 4th of pi over 4 is 1 to the 4th, and 1/4 times 1, right, minus 1/2. This is going to be 1 squared, and then we have ln of secant pi over 4, which is ln of root 2. Good. And now we're going to take away, and we're going to do it again, and we'll have 1 over pi times 1/4 times 0 minus 1/2 times 0, and this is 0 to the 4th power, and this is 0 squared. And then we have plus the ln of 1. And the ln of 1 is also equal to 0. So this whole expression is equal to 0 because every term on the inside is equal to 0. So our final answer here is going to equal 1/4 minus 1/2 is minus 1/4. So we can put that on the other side, and we can say that this is 1 over pi times the ln of root 2, take away 1/4. Good? All right, so hopefully that does it. Please take a look at your table of integrals. They're very quite interesting. If you are going into physics or engineering or other types of applied sciences, it is worth it to practice applying the table to calculate various integrals and recognizing those patterns. And please note that oftentimes you will need to make a u substitution before you can proceed with evaluating the table. And when making u substitutions, don't forget that you either need to back substitute or you need to make a special adjustment to your dx so that you can make a direct substitution for du.